All right. Go ahead and have your homework handouts out. Just 7 problems from this chapter. There's not a ton of math in this chapter. Chapter 7 was pretty much all math, very few terms. Chapter 8, a lot more terms, a little less math. Really, the math you need to know the equation for force, class. F equals ma, that second law of motion. And how you can rework that particular problem, because you can work it around a few different ways. You need to know your friction force equation.
It's like FKF.
What was the last F?
F sub m.
There we go. Okay, so we got F equals ma and all of its derivatives. We got force of friction is mu times normal force. Now, if it's SF, it's mu sub S. If it's KF, it's mu sub K. But in general, coefficient times normal force. And then we had gravitational force. And gravitational force was F equals?
G times the quantity of m1 times m2 divided by r squared.
There we go. And we do need to, of course, know that G is?
6.6730. Sometimes newtons.
Negative very important. Newtons times meter squared over kilogram squared. Okay, so there's our basic equations. That's pretty much the math handout. Let's go and review some things, though, before we get into the math handout. We've been talking about Johann Kepler. He had 3 laws of planetary motion specifically. So Newton was plain old motion, general motion, and Kepler was planetary motion. Remember, we said his laws are empirical, his laws are kinematic, based on observation, really only describe what happens. His first law was called the law of orbits. It says
All planets have ellipses.
elliptical orbits, good. Planets go around in ellipses. Second law of planetary motion was called the law of areas, but it basically said that when a planet gets
Closer to the sun.
it's going to,
Speed up.
and when it gets,
Farther from the sun.
it's gonna,
Slow down.
what do we call the point where it's closest? Perihelion, furthest, aphelion. And the third law was called the law of periods, and it basically said what, Michael?
It's about the time the planets travel. The closer they are, the faster they go.
They didn't necessarily talk about the closer or the faster they move, but rather the closer they are,
The faster they are.
the less time it takes to get around. Yeah, less time to get around the closer they are. Newton explained most of that through inertia, and there's this force that drives the planet's movement. What force causes the planets to move and to keep moving around and around the sun? What force kind of holds the planets to keep them from just flying out further into space, class? Gravitational force, right? That gravitational force or gravity that the sun exerts on all of the planets in our solar system. And that's what led us to the universal law of gravitation. Basically, gravitational force, class, is directly proportional to what? The product of the two masses. So the bigger the two objects are, the more force there is. But it's inversely proportional to, well, by radius we mean what? Distance between their centers. So the square of the distance between their centers. So force, gravitational force, directly proportional to the product of the masses, inversely proportional to the square of the distance between their centers. Now, when we talk about their centers, we're talking, class, about the center of gravity, right? The center of an object's gravity. So we said every object has that one point at the very center of their mass. We call the center of gravity. Unless you're outside where gravity could affect you, then we call the center of mass, right? And y'all seen that little demonstration about the little birdie who can balance on his nose? You seen the little birdie on the nose? My little kids love this thing. It used to sit out, and I just remembered it. Otherwise, I would have shown it the other day. But I ordered something from a science place, and they sent it as a free sample. My kids like it, if I can find it. Yeah. So, got a little birdie, and you can balance him on his nose, like so. You can't balance him anywhere else, but you can balance him on his nose, And why can you balance? You get to balance them on the nose. You're wearing purple. Birdie's purple. All right. How can you balance on the nose though? That's the center of where his gravity is. So we have the tail of the bird and the wings of the bird have a little bit of gravity behind the bird, but we have the wings stretched out in front so that the weight is forward, right? So you can balance the little birdie on his nose. Even comes with a cool little stand so you can like just leave him sitting around, balancing on his nose all the time. And my kids love it when they come in and see the birdie balancing on his nose like that. So anyway, shout out to my kiddos and the little birdie. All right, anyway, but there's that one point in the tip of his beak is his center of gravity. Now, not the case for you, though you can change the position of your center of gravity, right? If you were to hold your arms upward, that would shift your center of gravity higher. And there are things you can do, I suppose, to shift that, depending on how you proportion your mass. But yeah, we said that that center of gravity or your center of mass needs to be supported, right, by a base of support. And as long as it's supported, we have what we call static equilibrium. Now, as long as that center of gravity is well supported and the object would not be easily knocked over or tipped over, we would say we have stable equilibrium, a large base of support. However, if the base of support is very small, so that the object could be knocked over at the slightest disturbance, we have unstable equilibrium. And if the object is in such a position that you could move the object, you could overturn the object, but the center of gravity wouldn't even lower, that is, the object could basically roll, then we have neutral equilibrium. So stable, there's a good base of support. It would take a significant force, a notable force, to knock the object over to lower that center of gravity. Unstable, it's precariously balanced. I don't know if you've ever seen the demonstration where you can balance an egg on its top. Ever seen that? Apparently at the equinox, you could balance an egg. And my science teacher did that, and she left it sitting in the fume hood. She closed the fume hood so nobody would touch it. It was sitting there, balanced on its end, right at the equinox. It stayed that way for like 2 weeks. And then I think it began to smell, so we got rid of it. Anyway, something like that. Anyway, and then neutral equilibrium, the object's center of gravity. I mean, you could disturb the object. The center of gravity is not going down because it's already at its lowest point. It's a rolling object. And then, of course, if the center of gravity was outside the base of support, then the object, we would say, is in a position of instability. So there's a sense of stability when the center of gravity is supported. Even if, like in this case, I mean, I've got a very small center base of support, but I'm still over the base of support. Okay, if I'm not even over the base of support, I'm in a position of instability. And we said the object will typically fall over unless it is, for instance, you sit on your bike and you lean to the side, you fall over. But you can lean on your bike and not fall over if you are moving forward at the time, right? You have a certain amount of inertia that kind of keeps you going despite the lean that you did. Now, you can lean too far even for that, but yeah, instability is where that center of gravity or center of mass falls outside the base of support. All right, that's all from our last lesson or so. Let's take a look at the homework handout. And you did it on paper. And you did it on the handout. And you did it on paper. I'm looking here, I'm like, there's a 1 through 7 on the paper. And I see a 1 through 6 on the Duoflanger. So one of these somehow got skipped. We'll see if we can figure out which one it is. We'll have you help me with that one. Number 1, go ahead and read that for us if you would, Audrey.
Find the force necessary to accelerate a 260 gram mass, 13.5 meters per second squared.
All right, so we're given a mass, we're given an acceleration. How do we find force, class? And now the only thing is, one of those numbers ain't right, class. The grams, got to change it to kilograms. So we move the decimal 3 times. And what do we end up with for the force, Audrey?
3.51 newtons.
How many sig figs? Only 2, because the 260 grams has only 2 sig figs. So make it 3.5 newtons. Sneaky, sneaky who wrote this. All right, number 2. Force of 83 newtons is exerted on 18.4 kilogram mass. Find the acceleration. So we know the force, we know the mass, we need the acceleration. What do we have to do, Kendall?
You divide away the m.
Divide away the mass. And so if we take the force divided by the mass, what do we get for the acceleration, Kendall?
4.51 meters per second squared.
Good. This time we do have three sig figs, so 4.51 meters per second squared. Number 3, force of 175 newtons accelerates an object at a rate of 7.6 meters per second squared. To find the mass of the object. Well, we have the force, we have the acceleration, we need the mass. What do, Michael?
M equals F over A.
M equals F over A. So we divide the force by the acceleration. What do we get for the mass?
23 kilograms.
Good. Rounded to two sig figs, 23 kilograms. Questions on 1, 2, and 3? We good on 1, 2, and 3. Number 4. If a force of 34 newtons can accelerate an object at 12 meters per second squared, determine the acceleration of the same object if the force is increased to 50 newtons. So we have two different forces, and it says the same object. Well, if the object doesn't change, then we can assume, class, there's no change in the mass, right? Force on the mass can change. Acceleration of the mass can change, but an object will not spontaneously change its mass. Now, if you are the mass, you can at Thanksgiving change your mass spontaneously. Well, it's not entirely spontaneous. Anyway, so here, since we have two different forces and two different accelerations, but one consistent mass, how could I rewrite my equation here, Audrey?
F1 over F2 equals A1 over A2.
Good. We could say M1A1 over M2A2, but the M's are going to be the same, so they're going to cancel anyway. So we've got the first force is 34 newtons, second force is 50 newtons. Notice the newtons and newtons will cancel. The first acceleration was 12 meters per second squared. We need to find the next acceleration. We'll cross multiply. We'll get?
18 meters per second squared.
Good. Rounded two sig figs, 18 meters per second squared. Are we good on that one? We are not. Is that the one you skipped, Michael?
No, I got all of them. I just forgot to number one.
Ah, okay. Okay, questions on number 4. Number 5. I'm going to read that if you would, Kendall.
Two men get together to push a car with a mass of 1,200 kilograms out of a ditch. As they push, they accelerate the car from rest to a rate of 2.53 meters per second after 3 seconds. How much force are the three men combined exerting on the car?
All right, so as we look at this one's a little more involved because we've got a mass of 1,200 kilograms. The car is at rest initially, class. That means but it's going to reach a rate, it says, or of 2.53 meters per second, and it's going to take 3 seconds to do that. All of this I can use, class, to find acceleration. And once I know acceleration, I can find force. To find acceleration, of course, we'll use the acceleration equation. Does anyone have the acceleration written down somewhere on the paper? Michael, what you got?
0.843 repeating.
Yeah, it comes to 0.843 repeating meters per second squared. And then we're back to the F equals ma. Just multiply the mass times the a that we just got. And what do we get for that force, anyone?
1.01
At 1,012 newtons, but I think we're only allowed how many sig figs? 2. So not 1.01, but just 1.0 E3 newtons would have been our answer there. Questions on number 5. Numero 6. 2 parts to this one. We got a wooden box, 275 newtons, sits on the floor of a shed. We're assuming the shed is sitting level. It doesn't say that it is. But we don't know how to solve it if it isn't, so let's just assume it's level. But that sound good? Next chapter, the floor won't always be level. But in this chapter, we're going to assume level floor. So 275 newtons. If that's the weight of the box down on the floor of the shed, class, then assuming there's not dry rot and it's falling through the floor because it doesn't say that, how much force pushes back up?
1.0.
If there's 275 newtons down, how many newtons up?
275.
275 newtons. Now the downward is what we call the weight. The upward is called the normal force. And let's see, it says assume it's a dry wooden floor. So I said to go back to page 117 in your textbook. And we want wood on wood that is dry. And we said to start sliding wood on wood that's dry, coefficient of static friction, class, is 0.62, and the coefficient of kinetic friction, dry wood on dry wood, is
0.48.
0.48. So to find the force of static friction, the force required to start sliding, just multiply. And what do we get for the force to start sliding the box, Michael?
171 newtons.
I got 2 sig figs from the coefficients, though. 170 newtons. And then the force to keep sliding it, once we've got it moving, 170 newtons starts it, and then we can back off the force a little bit if we want to, because it only takes, Audrey, 130 newtons to keep it going after that. All right, questions on number 6? Yes, sir.
So it was 2 sig figs?
Well, yeah, in the chart, the numbers we had to look up were 0.62 and 0.48, which is 2 sig figs.
Okay. I was going off the number in the problem.
Right, and the only thing was I was too lazy to actually type the numbers in the problem, so I made you go look them up, but they're still numbers we used in the calculation, so yeah, that's why. So, mental note for test tomorrow, right? If we have a chart that we're using, numbers off the chart also affect significance. Number 7. A boy walks into his bedroom and runs into the dresser. That ever happened to you, Michael? All right. He claims that gravitational force caused him to do so. The dresser sits 2 meters from the doorway, has a mass of 72 kilograms. The boy has a mass of 93.4 kilograms. He's about a 200-pound kid, about a 150-pound dresser full of stuff. How much gravitational force was actually responsible for the collision? And in all probability, sheer clumsiness was the real cause of the collision. At least that's what we will speculate. Well, if we're finding how much gravitational force, obviously, class, we need the equation. F equals G times m sub 1 times m sub 2 all over r squared. And so we already know the G, right? That's going to be the 6.673. M sub 1 class could be the dresser, which is 72 kilograms. The M sub 2 could be 2.4 kilograms, the boy's mass. And then the R would be the 2 meters away from him and the dresser. Now again, distance between the center, whatever, let's just use the 2 meters, and we'll square it to get 4 in the bottom. So we multiply, divide by 4. We end up with how much gravitational force here, Kendall?
1.12 e⁻⁷.
Yeah, that's not even millionths of a newton, and a newton's already small. It wasn't the problem. He's just clumsy. All right, questions on these? All right, set that aside. Let's go and review some terms from chapters 7 and 8. Chapter 7 was all about vectors, remember? And what is a vector anyway? Audrey?
It contains magnitude and direction.
Good. Any quantity that has both direction and magnitude. Oh, yeah. Okay. We talked about vectors that act along the same line, class. Collinear, there we go. We talked about vectors that act at right angles. Perpendicular, we talked about vectors that are not along the same line and they're not at right angles. Skewed vectors. And we said for collinear vectors, if they're going in the same direction, we could also refer to them as being parallel. So parallel collinear vectors, what would I do with their magnitudes? Add them. And of course, we keep the same direction. And if they were going in opposite directions, class, we refer to those as being anti-parallel. And we're doing with the anti-parallel collinear vectors. Subtract them, but keep the direction of the greater one. Whichever was greater, keep that direction. What we're doing then is finding a single vector that shows the outcome of the other vectors. What do we call a single vector that shows outcome? Usually labeled with the letter R. Resultant, the resultant vector. And these multiple vectors that act at the same time on the same object can be referred to as concurrent vectors. Concurrent vectors. We said perpendicular vectors. If we're finding the resultant, we need to start by finding the magnitude of the resultant. We got a vector here, we got a vector here. The resultant can be found in class using the Pythagorean theorem. And then the direction based off of the primary vector is this angle. In this case, if this is east and this is south, class, the resultant is to the south of east. And this angle would be whatever degrees south of east. How would I find the angle? Arctangent. You'd use the arctangent to find that. With skewed vectors, we had a couple of laws that we could use. If we wanted to find, for instance, we've got something here and we've got something here. Okay, there'd be some angle phi, for instance, right here. How would I find the angle theta in this particular instance? Subtract from 180. And then to find the resultant, we have to use the law of cosines, which c squared equals a squared plus b squared minus 2ab times the cosine of c. And then to find this angle here, which we'll call alpha, to find this angle, we'd have to use the law of sines. And then we said, no. Look at this vector and say it has a certain amount of x and a certain amount of y. Well, in this case, it's all x, no y. This vector here has a certain amount of x and a certain amount of y. And we could take the two x's and add them together. We could take the two y's and add them together. And we get a single x and we get a single y. And we're back to Pythagorean theorem and arctangent. So really, do we need to use the laws of sines and cosines at all after all? Not really. We don't really need those anymore because we're well, at least not for this, because we're able to go with components instead. Now, as we find components, for instance, this here, this vector has an x component. Relative to the angle, the x component class is the adjacent. And of course, the actual vector is my hypotenuse. What trig function should I use? The cosine, where the y vector in this instance class is the opposite. And of course, we have the hypotenuse, so what trig function should we use for the y? The sine. So remember, so kato, a sine is the opposite over hypotenuse, cosine the adjacent over hypotenuse. We also use this component method to deal with the motion of objects that are launched or hurled through space. What do we call these objects? Projectiles. And the path of a projectile's flight is called the trajectory. There we go. The trajectory and the trajectile. Don't do that on the test just because I said it. But to the trajectory. And we said that for a projectile, if there were no air resistance, the path of a projectile would always be in the shape of a parabola. Now again, students sometimes like, I just got to memorize shape is, well, hold on. Projectile shape is parabola. Planetary shape is ellipse, okay? So don't just lock in on shape means this, because there's two different shape questions that we've worked through. We didn't actually talk about it. You read about escape velocity and critical velocity. Critical velocity gets you into orbit. Escape velocity gets you all the way out of Earth's gravitational attraction, so you can fly to other planets like Mars and such, or fly to the moon, whatnot. We don't really need to know that. Obviously, Newton's three laws. First law is called the law of inertia. Says an object tends to retain its velocity unless outside force acts upon it. We said that second law of motion, acceleration depends on two things. Force and mass. Acceleration, directly or indirectly to mass? Indirectly or inversely, right? And directly or indirectly to force? That's directly. We said the pull of gravity on an object's mass is called weight. So to find weight, mass times gravity, right? M times G. Third law said for every action there's an equal and opposite reaction. Resistive force that arises when an object slides across a surface or through a medium. Friction that has to be overcome to start sliding. Friction that has to be overcome to keep sliding. Which is bigger? Four laws of kinetic friction. Friction does not depend on velocity. Moving it faster will get the job done quicker, but moving it faster doesn't actually give you less friction unless you're dragging like extremely slowly where you haven't actually overcome static friction yet. Well, then obviously you're still battling static friction, so we're not to the laws of kinetic friction yet. I digress. But velocity doesn't affect it. What else doesn't affect it?
Area.
Surface area. It doesn't matter if you get more of the substance on it. It really doesn't matter. It does very much depend on the types of surfaces. Rough surfaces are going to have more friction. Smooth surfaces is going to have less, right? And then the fourth thing, friction very much depends on. If it's a level surface, it does. In general, friction depends on the normal force. But it's not up there anymore. Remember the equation. Mu coefficient is the types of surfaces times normal force. We said we could reduce friction, because sometimes friction is not so good. Now, sometimes friction is very important, right? Right? When you're driving, you want friction. In fact, remember we talked about with Bernoulli's principle and the airfoil on the back, the wing on the back of a race car is designed to get more air pressure pushing down, which adds to the weight of the car, right? So if the car just sits there on the road, the car may weigh, say, 1,000 pounds. Road pushes back up with 1,000 pounds, right? Equal and opposite reaction. There's your normal force. But if as it's driving, as it increases its speed, if that wing forces more air pressure pushing down, now the car not only has its own 1,000-pound weight, but maybe an extra 500 pounds of air pressure that are extra. Well, that means the ground has to push up with more normal force, which increases friction force, so that it can make a sharp turn. So anyway, kind of connecting the two ideas there. But we said sometimes we don't want as much friction, right? If you want to skate around the kitchen and you don't want as much friction because that takes the fun out of it. So to decrease friction, class, we could lubricate. We could pour some water on the floor, some soapy water if you're really good with it, right? And then you could really slip and slide on the floor and or pour a little water outside, the store, and then you slip and fall and then sue the store and make money. Just kidding. I don't actually recommend that. I've heard of people doing that though. Purposeful slip and falls. Anyway, but you can lubricate the surface. Pour some water, soapy water on the floor. Boom, down you go. What's another way you could reduce friction?
Wheels.
Okay, if you were to roll around the floor, it wouldn't matter how rough the floor is if you're rolling around, right? So roll around the floor on wheels. Another way. Choose more suitable materials. Instead of getting the floor all soapy and wet and making mom mad, just put on soft fuzzy socks instead of your rubber-soled shoes and you'll slip and slide just fine. And then the final way, let's suppose it's a wooden floor. Minimize the roughness, sand it down smooth so you can, I still can't see my slipping and sliding around on a wood. I guess if you smoothed it down and waxed it too, that would minimize roughness. Maybe you could slip and slide on like a hardwood floor. Yeah, nice waxed hardwood floor might allow you to slip and slide a little bit there. Anyway, fundamental forces of nature, class. We got the gravitational, strong, weak,
Magnetic.
electromagnetic, the strongest of all,
Strong.
the weakest of all.
Gravitational.
Which one's always attractive?
Gravitation.
Gravitational between
Bodies.
any two masses, any two objects. Which one is sometimes attraction, sometimes repulsion?
Electromagnetic.
Electromagnetic. And if you have like charges, repel and opposite charges would attract. Which one is kind of a non-attraction, and it explains why certain behaviors exist in radioactive decay, specifically like with the antineutrino. That's the weak. And which one is what really holds the nucleus of an atom together? Strong force. The belief that the Earth was the center of everything. The sun is the center of our solar system, and everything else we already reviewed earlier. Let's go and take a look at one more handout now. And let's take a look at some more math. And if you're watching on YouTube, of course, this is in the description of the video. Handouts are always in the description of the video. And back in 2014, we weren't doing so hot. Look at that date. That was a down year. Anyway. Not picking on the class of, well, actually, that would have been the class of 2015. Anyway. But I digress. At your seats. Get started on the first problem. Take a few moments to work, and then I'll start putting it up on the board. Draw pictures. trying to make a hurricane on the bird, and the bird was unaffected by hurricane.
What about a monsoon?
My fan doesn't do monsoons. Well, I guess if I were to like spit water or entrain water, use my double straw, then we could get some. Anyway. Do we start our picture like this on the first problem? Shake, rattle. So is he shooting it up or is he shooting it forward? Yes. Some of the initial velocity is forward. Some of the initial velocity is upward. You've got to find the two pieces first. Find those two components first. Once you got your components, check and see if you're on the right track. Audrey says she's got them. Kendall's got them. Michael's got them. Which of these two components do I work with first? Always, always, always.
Y.
The y. And it would not hurt to make a chart where you separate your x pieces and your y pieces. I know initially in the y, 33.75 meters per second. I know in the x initially, 69.20 meters per second. But there's other things we know about the y, which is why we work with the y first. Did you get the rest of the yellow stuff on that chart? At the high point, the final velocity in the y, and not in the x, just in the y. Acceleration in the y, it's being pulled downward till it gets to that 0 point. Therefore, we can use those to find the time it takes to get up. How many already have the time up? Everyone's already got it. Okay, did we get 3.44 blah, blah, blah seconds up? All right, now, what goes up must come down. How long is it going to take to come down?
6.5.
It's going to take a total time of 6.88 blah, blah, blah seconds, isn't it? And you realize that could be in both components, couldn't it? What else do I know about the x?
It's an average velocity of 68.
Yeah. This is the final velocity of the x. It's the average velocity of the x. They're all this, right? And if I know the time and I know the average velocity, I can find displacement in the x. Just multiply velocity times time. And that's how we finish it out. Now, obviously, this is drawn a little unrealistically because the angle wasn't nearly this steep. It was only about a 26-degree angle, not a, what is that, almost a 50-degree angle, 60-degree angle. Anyway, what's the displacement in the x? might round it off to, how many sig figs?
2.
2. So we'll round it to,
4.
it's a pretty good shot. Questions? We're going to be able to do this tomorrow. If something is shot up into the air or thrown up into the air, we're going to be able to find the time it takes to get up, double it to get the total time, and then find how far it flies. What if I wanted to find how high it rose? Well, that would be what? That would be d sub y. Again, don't touch the x. If you wanted to find d sub y, you use one of those equations to find that d sub y, wouldn't you? But don't let the x's and y's get mixed together. Get your components, keep them separate. Questions on that first box. Go to the second box and get started on that one. It's a swirling cloud of dust. My eraser's clean now. Just vacuumed my floor yesterday. Of course I dropped the eraser. Haven't vacuumed in a week. Don't drop an eraser until I vacuum. It's Murphy's Law. Saying hi to Miss Davidson downstairs. Is the bomb traveling forward or is it traveling downward, class?
Yes.
Before it's released, is it traveling forward or traveling downward? It's only forward. Once released, it begins to go downward, right? But initially, is it going downward? No. Initially, it is all forward. Do you see the difference between this and the last one? If something is, now if I threw something down at an angle like this, if I threw something like this, am I throwing it forward or downward? Yes. That time I really am throwing it forward and down. Like a dive bomber, right, is already going down at an angle. So the bomb, as it's released, is already going downward and forward, right? In this case, the bomb is not going downward yet. It's only going forward. Now, why does it go downward? Gravity. That's going to finish out your y. So finish out your y column. Do we finish out the y column correctly? We identified that the 1,500 meters is displacement in the y, and that the acceleration in the y is a positive 9.80 meters per second squared. Why was it negative last time?
It was going up.
Because last time it was going up and gravity was working against it, right? This time it's just going down, gravity's working with it. We could find final velocity in the y, we don't have to, but we will need time, right? We need that for number one, how long does the bomb take to hit the ground? So whether you find a VFY or not, you need to find the time. And again, it's using the y. Again, you can find it without the VFY. A lot of times we seem to like to get the VFY first. Anyone do it by finding the V sub Fy? Is that what you got for your final velocity, the y? Okay. The important thing though is the time. Do we all have the time now? What do we get for the time? 17.49 blah 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 seconds. Now that is one of the answers we need, so we're going to round it to how many sig figs? 2 sig figs, so we'll say 17 seconds. And there's our first answer. Now, do we need to double it?
No.
No, because that which goes down goes boom. It doesn't go up again, right? So it just goes down, so we don't double any time. Now, this is the initial velocity in the x. What else do we know about the x? They're all going to be that because there's no acceleration in the x, right? So if I know the average velocity in the x and I know the time, which is the one thing that can go between components, I can find the displacement in the x. Plane is being ignored in this picture. There's just the bomb. We have X-ray vision. We can see the bomb inside the plane, and we see the bomb go boom. Okay? How far ahead of the target should the bombardier release the bomb, class?
About 2,600 meters.
About 2,600 meters. 2,624 point blah, blah, blah. There's our final answer. So 2 answers. 17 seconds to go boom, and then 2,600 meters to go boom. Questions on this type of problem? The projectiles, that was really the focus of chapter 7, was working our way through. Everything led toward projectile motion. Questions at all? All right, the next box should be pretty straightforward. Another review of a friction problem. Got a 325 Newton desk going across a carpeted floor, which the desk and the floor have a coefficient of friction of 0.427. Once he's got the desk sliding, what minimum force is required to keep it moving? And Kendra, what you got? 139 newtons. Is that what the rest of us had as well? Question, Audrey?
I think I divided it wrongly.
But there actually shouldn't be division. Remember, we're finding the force of kinetic friction. So we just take that coefficient and multiply it by the normal force, which the weight and the normal force will be the same since we're on a level floor. Does that make sense? All right, look at the next one. Force needed to accelerate a 7.4 kilogram object, it's about 15 pounds. So we're trying to throw something that's 15 pounds and accelerate it at 2.5 meters per second squared. How much force is that going to take? And we will have Audrey call it when she's got it.
18.5.
Good, rounded to
19.
force measured in
19.
19 newtons. Good, just use the equation class F equals ma. For the next part of that same box, find the acceleration of a 35 kilogram object exposed to a force of 58 newtons. So a 35 kilogram object and a force of 58 newtons. Finding the acceleration. And Michael, call it when you've got it.
1.7 meters per second squared.
Good, what equation do we use, class? F equals ma, but A equals, if F equals ma, then A equals
1.6. Oh.
F over m. There we go. So divide the force by the mass, that's where we get the 1.7 meters per second squared. If a t-shirt cannon can accelerate an extra large shirt, that's for a very attractive person, with a mass of 0.54 kilograms at 24.1 meters per second squared, what acceleration could it give an extra small shirt, a Kendall shirt, that has a mass of only 0.36 kilograms? Yeah. So it shoots a double XL t-shirt pretty fast. Launch it, accelerates it out of there. So what about an extra small shirt? Making that section of the stadium the nosebleed section. I'd get hit in the face with it again. I always thought t-shirt launchers were cool. I'd give me one of them. And Kendall's going to call it when she's got it. Is extra small herself?
16.1 meters per second squared.
That seems weird though, because like a double XL t-shirt, you should be able to fire an extra small faster, shouldn't you?
Yeah.
What equation did you use?
I said it, but it's like the F1 over F2 equals M1 times M1 over M2.
There we go, but it's the same t-shirt launcher, right? Whatever spring or air mechanism it uses, I think it's an air mechanism, to fire that t-shirt is the same regardless, right? So if the forces cancel, then it's going to give us a 1 over 1 equals M1. What are we going to have to do?
You're going to have to multiply
To get,
M1 times M1 equals M2 times M2.
yeah, there we go. So plugging it in like that. Who did that? You did. She's fixing it. We'll give the ladies just a moment here. Yeah, that extra small is really coming at you. And what acceleration coming out of that t-shirt cannon are we getting? There we go, and then rounded to 2 sig figs we get.
36.
Is that what we got now? 36 meters per second squared?
I just left it as is and did M times A over.
M times A, and then you cross multiply still.
I didn't cross multiply.
You did
I
not
kinda
cross
just did-
multiply.
I just did the first two numbers divided by the bottom one. I kind of,
Made it work.
yes.
Okay, all right. Questions on that? All right. Test tomorrow. No written homework tonight. Your only homework is do what you need to do to be ready, whether that's rewatching video, studying, memorizing, whatever you got to do, be ready for that test in our next lesson.